As a chemist, one of the most important places that we can see uncertainty in measurement is in using glassware. So your first skill needs to be being able to read that glassware as was designed by the manufacturer. So we know that different pieces of glassware have different levels of accuracy and precision built into them. But you need to be able to read one individual piece of glassware as accurately as it is designed to be read. When you're looking at, for instance, this piece of glassware, you'll notice this kind of double bubble area. That is due to the cohesion and adhesion between the solution in itself and the solution and the glassware, which creates that kind of, well, double bubble thing. That's called a meniscus, which sounds like the thing that's in your knee. It's not the thing that's in your knee, but this is very common with most solutions when poured into glassware. And when the manufacturer created the glassware, they did so with the assumption that everyone was going to read the meniscus the same exact way. And that is by reading the bottom of the meniscus. Okay, so this is just the accepted way to read glassware. All chemists do it the same way. If you read the top of the bubble here, you'd be doing it incorrectly. Even the middle would be wrong. The idea is to get down at eye level with the glassware, put the piece of glassware on the countertop, and then you're supposed to read the very, very bottom of the meniscus. Notice if you don't do that, you'll end up with some incorrect readings, which is just going to introduce a whole host of problems. So once you know how to read your glassware correctly, then you can interpret it with the significant figures. So what are significant figures and what are they used for? We report measurements using significant figures to communicate how accurate a measurement is. So if I said between you and me there's about 200 feet, just in the way that I say that, you can tell that it's an estimation. Okay, that number, about 200, technically could be as few as 150 and as many as 249. Anything in that window is going to round to 200. However, if I say, hey, there's 201 feet between you and me, just by adding that extra detail, the assumption or the implication is that I went out and I measured and it is 201 feet. Okay, so each of these has 3 digits, and that's another word that you'll hear instead of figures. You might hear the word digit. You might hear significant digit. They each have 3 digits, 200 and 201, but the question is how many of those digits are significant? And another word for that is how many of them are actually measured. In 200, and we'll go over this later, but in 200, the only significant digit is that 2. The 2 zeros are not significant. Okay? In the number 201, all 3 of those digits are significant. All right, so even without having a full understanding of what significant figures are, you can tell that this number here, 201, is a better measurement than about 200 feet. Chemists and scientists in general want data that has more significant figures, okay, because it implies that there's better measuring going on. All right, so the quality of significant figures depends on the lab equipment quality, and here's how we apply them. Most commonly with glassware. So more precise glassware has less air built in. So more precise glassware would be things like a volumetric flask or a burette. Less precise glassware would be like a plastic pipette or a beaker. Okay. When we have less air and more precise glassware, we have more significant figures that are a result of those measurements. Okay. Sig figs are expensive. Chemists pay good money for glassware that yields more precise data. So a beaker is going to be a couple bucks, a burette, a couple hundred. All right, so we pay for quality data. We will also use significant figures anytime we measure anything, even if it's just with a digital balance. And then in calculations. So we take our data, we process the data to get a result. The quality of that result is going to be dependent on the quality of your initial pieces of data. Okay, so here's where we can see this in action. Here we've got 3 different pieces of glassware. We've got a beaker, we've got a graduated cylinder, and we've got a burette. Obviously, or hopefully you can see that, it's a little hard with the burette, that they are all 3 filled with about the same amount of solution. Okay, they're all in the 38-ish range. our goal is to take as precise a reading from each of those 3 pieces of glassware as possible, and then compare them and see what we get. So if we look at the beaker, all right, we'll start with the beaker, which is this guy down here. All right, the beaker, it's not labeled, but we know that this is 30 milliliters right here. We see that the reading is between 30 and 40. That's the only thing that we can be totally certain about. Okay, so we get to put 30 for sure. All right, and then I have to estimate. I always get 1 degree of estimation. That's it. So I'm going to guess that that is an 8. All right, and that would be 38 milliliters. Now, the 3 was a certain digit. The 8 was my 1 degree of estimation. All right, that's all I get. I don't get to guess again. I don't get to guess off of my first guess. That's as far as I can go. Okay. If I compare that to my, this one in the middle is my graduated cylinder. Okay. We've got 30, so each of these increments is going up by 1. So once again, we are between, let's see, this is 38 and that's 39. This time I get to be sure about the 8. We've got a 3 and an 8, just like before. But this time I know that the 3 is correct and I know that the 8 is correct. What I'm guessing about now is the tenths place, and I'm just going to say maybe it's 38.7. And that would be in milliliters. Again, I only get to guess once. Okay, that's my degree of estimation. And hopefully you can already see, comparing the beaker and the graduated cylinder, it's not that the graduated cylinder is giving us a bigger number. It's not an inherently bigger piece of glassware. It's an inherently more accurate piece of glassware. And I'm getting more precise data from it. Okay. Last but not least, we have our burette. Okay, this is a piece of glassware that's in that to deliver category. So notice that the numbers are getting bigger as you go down the piece of glassware. So that's a little different. And then also notice that the big numbers are already the ones place. The increments, these little guys right here, those are tenths places, which is fantastic. So already we are at 38 point, and then if I look at the bottom of the meniscus right here, it's between 4 and 5. Okay. So I know it's going to be between 4 and 5, and then I get to guess 1 more digit, and I don't know. I'm going to say maybe that's a 6. Okay, maybe this is 38.46 milliliters. And let's go back. I was certain about the 3. I'm certain about the 8. I'm certain about the 4. I get that all from the glassware. The only one that I had to guess about was the hundredths place right there. Okay, again, not an inherently bigger number, but a more precise number. And a chemist will look at those 3 values and will really appreciate this one because of that extra precision. That means that you had a quality measuring device and a quality scientist taking those measurements who knew how to read the glassware correctly. We will get into talking specifically about how to count sig figs, but just so you know, it only gets tricky when you're dealing with zeros. The beaker produced only 2 significant figures. The graduated cylinder produced 3 significant figures. And the burette produced 4 significant figures. So always and forever, more significant figures is better. But we can't just create them arbitrarily. All right, that would be basically like lying about our data and the quality of it. We only get as many significant figures as we can get from the quality of our measuring devices.